Okay, so hello everyone, in person and online. I'm very excited to be here. I think this is great. It's a great initiative. Let me say that for 1 second before we start and we dig in. And I'm also very happy to have been invited to give this tutorial on AI interpretability. And I mean, I will try to do my best to bring you from zero to hero. You will recognize it is a bit of an impossible mission because the number of papers that have been written in the past decade on interpreting neural networks is quite large. So you will have a lot of reading to do after, but I guess we can get started with no further hesitation and just dig into the things. And then I will be around for the whole day, and I'm really happy to talk about any of the methods that I will mention later on. Yeah, I mean, I had a little introduction, so I guess you all know more or less who I am. But I just wanted to mention that some of the things that I will be showing in these slides will not have been possible without the collaboration with other brilliant people. Some of them are listed at the bottom of the slides, so please go check their work because they're also very interesting people. Okay, let's get started. So I couldn't put the video up. I was struggling because this comes from OpenAI website and they don't let you download the videos. But if you have time, I will maybe share the link or try to put the link on the chat. Please go have a look at this video because it's really a lot of fun. So they're working on reinforcement learning algorithms, and they were trying to use some video games to try this to train these reinforcement learning algorithms. And the objective here is like, this is a boat race, and the objective is to win the boat race before any of the other participants. So you want to do it to finish it in the earliest time, and you want to beat all the other competitors. And what they found is that the algorithm, when it's trained on this game, it actually learns. It finds an area in the region where the game was placed, where you could actually just start spinning your boat over and over again, destroying all the other boats. And by destroying all the other participants, you actually get to win the game with more points. So, I mean, this is just really fun. It's a super fun video, but I think it also points up a problem of when we train these models, that is the problem of alignment that is becoming bigger and bigger in the domain, and is the problem of the fact that we might have multiple objectives, and we might have aligned AI systems that advance towards the main objective, but it's actually difficult to verify whether they are aligned in all senses, and they can also advance towards other objectives that are not the intended ones. So in this case, the objective of the AI system was just to win the race, but it had no values incorporated about the fact that it's actually not fair to destroy other people's boats, for example. So if we were to apply this type of mechanisms in reality, we would be facing a problem that is, we need to think of all the possible things that are going to happen. And I think it's really hard, and it might even be impossible to specify all the important values and constraints that populate our real world. We live in a complex society with a lot of unwritten rules that is difficult, and it's difficult to take them and just incorporate them in machine learning models. And what we're seeing is that the AI doesn't have the same complex structure, so it easily finds loopholes and it gets faster to the objective, but that could be harmful. And another problem that comes with AlAlignment is not only on the learning algorithms per se, but it also comes from the data. And I don't know if all of you work in medical imaging or in the medical domain, but I think if you do, you're familiar with the fact that the data collection that we're working with is very often imperfect. It shows inequalities. Think about it. The way we collect data, we have access to large amounts of data also because of the geographical location where we have the chance to be working in. And so naturally, we have inequalities in terms of race and gender. And if you think also about some types of diseases, they appear more rarely. So they are part of an inequality that is, as of default, you won't observe more samples of a certain disease simply because it doesn't happen more frequently in real life, in a real world. And not accounting for these inequalities might actually cause problems, might have a harmful impact on the people. Think about not accounting gender in clinical trials that turned out in diagnosed diseases, or the adverse drug reactions that happened in some real clinical trials. How can we avoid those things? I think this per se stands as a motivation of why we need reliable AI. and why we should be looking for biases, confounders, and robustness to distributional shifts, for example, for applying our models to data sets that we were not able to train on, or for data sets that we cannot account because we won't be able to see them in advance. For example, when a new patient comes in the lab, in the hospital. And I think that one of the main focus of my work has been really on enforcing the fact that the structure that we have in the society is part of human-centric decision-making, and it's actually the key to solve all of these. It's a workaround to solve all of these problems, because in the end, we're building tools that will be used by domain experts, and the domain experts are attached with the legal responsibility as of now for the decision making. So if we had an AI system that was predicting the progression of a patient, in the end, whatever choice is made by the clinician and by the doctors, by the oncologist, and they are attached with the legal responsibility for that. So we need to be able to provide these people not only performance metrics that reassure them about the fact that the model is working correctly on a few patients that we had in the test set. We need to provide them with something else that can give them complementary information to build a mental model about how the model is working, where they should trust the model, when they should trust the model, and why. And when also they're expecting the model to fail because maybe it was never trained on a particular subset of the population, for example. So I think here one thing, and this will be the last word, I think, about the introduction on why this is important, is I guess you're all here because you know that it is important, so I'm not trying to really convince you. But I think it's important to see this as a larger pool that instead of using safe AI and going towards AI safety. And there are multiple figures that populate this domain. It's a domain that is not filled only by computer scientists, but it's also filled by social scientists. So for example, by lawyers or ethicists that have more competence in some domains and that can help us to bring these values into the systems that we're building. And if you look at how I structure things here, you will see that to get to safe AI, we need to work towards reliable, trustworthy AI. And in fact, interpretability, transparency, and the incorporation of causal links that is maybe some of the most difficult things that we're trying to do right now in machine learning, lays at the bottom as the foundation for AI safety. So I think we really need to start from the bottom and start looking at these things in detail and then build slowly up our ladder towards creating a system that has some kind of guarantee for its safety, meaning that even in the case it's going to fail, we know that no harm is going to be produced because systems can fail. It's just about assessing the boundary of how much we can safely make a mistake. So what is interpretability? I checked on Wikipedia multiple times when I was doing my PhD. And I think this has to be in this tutorial because it's never clear. And one of the things I've noticed is that actually in mathematical logic, there is a definition. And it connects some formal theories. And let me just rephrase this for you in what it could be interpretability for AI. And this is a definition that we propose to the community. And we are waiting for feedback on that. I mean, the paper was published, but I'm expecting people to reply to that. And I'm encouraging people to reply to that because I think this has to be a discussion. And altogether, we can find actually a correct definition for interpretability. So we decided, I mean, we state in this paper that an AI system is interpretable if it's possible to translate its working principles and outcomes in human understandable language. And we will get to that. We will get to what is human understandable language. But I think the most important thing here that we should pay attention to is that in the end, we don't want to really affect the validity of the system by creating a translation. So if I were to explain what a model is doing, I want to stay as loyal as possible to this translation. And I mean, the definition can be relaxed to include approximation of the system. So think here of this curve that you see here at the bottom, at the top of the screen. I don't know if it's clearly visible, but let's say that is your decision function, right? Your complex, funky decision function that you've learned with your super complex model. One way of thinking of an approximation of this model that is easier to interpret is by dividing it into its tangents, right? And to have a linear expansion of that model. And that is much more interpretable because you see how much each of the features when you're doing this linear approximation corresponds to the inclination of the line that you're learning. So I think this is the point that I want to make here is that we can simplify complex models into something that is easier to interpret. And it's easier for us than just create simple models from the start, but we need to take into account the fact that in some points, the linear X function will not be as faithful to the actual decision function as the decision function itself is. So if we could build a decision function that is interpretable from the start, that would be the optimal scenario. And this is what this definition is kind of saying. So for today, I think I wanted to structure this talk as a little walk among all the techniques that have been built. And again, complete list is too ambitious. If you want to see all the list of methods, there are long reviews about that. But I'm trying to give you my perspective and a way to kind of orient in this big landscape of techniques that has been proposed. And I think starting from the bottom of this high mountain, what we actually want to do is we start from understanding the data. We want to first analyze the data. We want to make sure that we are aware of what are the limitations of the dataset collection that we're working with. And then we can go up on this ladder, and what we see is that we can move from something that is called mechanistic interpretability, so trying to understand what each component of the model is doing, to something that is post-hoc explainability, so working with a model that was already trained and trying to generate explanations for a user. Concept-based interpretability goes in a similar direction, and then eventually trying to work our way towards those that are called glass-like models, so models that are interpretable by construction, or even the incorporation of cause-effect links in our models. And I think for anyone who's starting, a very easy distinction to start making when looking at all these models is what kind of explanation or interpretation is even at the end. What's the output of the method? Is it a local explanation? So given an input image, you get an explanation that is valid for that input image. So what's the model looking at in this image? Or is it a global explanation that tells you something that is true for a set of inputs, like maybe images of one class, or even an explanation of the entire model per se, like it can be a translation of a deep learning model into a set of rules. So those are two differences that it's good to start making when looking at these methods. So starting from understanding the data, I think there are a few techniques that I want to mention that are not just PCA or UMAP of the data that you're working with, and is understanding what kind of examples can explain the data, and also what kind of example can explain the data according to the model representation. And so one of these is a maximum mean discrepancy. This is an old method, was proposed by Bin Kim during her PhD, I think. And the idea here is really that we should be focusing on what's the prototype of a class, for example. So what's the most common example of a class that you would see? And you can see, like in this case of a cat, it's quite easy. It's very likely that we see an image like this when we're looking for an image of a cat. But also we need to start considering all the underrepresented bits. So all of these type of examples that are lying in the long tail of our data distribution that we don't observe that frequently because they have something weird. They're something different. And these examples, we also need to consider them and take them into account when we're building models. So I think this is an important method to start looking at. And this is, again, is a reinforcement of what I was saying, that this is the ImageNet dataset, and there's people who studied actually the long tails of ImageNet, and also all the annotation mistakes that were done on the images in this dataset. And I think something similar would be extremely useful in the medical case, because we are working constantly in a case of long tails. So that's, I think, I think it's a global exploration of your data, and I think it's an important starting point for interpretability. Now, the second thing is mechanistic interpretability, and this has maybe even longer history. So here we are trying to understand what a neuron, a channel, or a layer are learning, and how are these patterns used. So if we look in the literature with the temporal scale, what you see is that the convolution operations were proposed by Zeller and Fergus in 2013. So where they were taking a convolutional neural network, they were taking a precise layer, And they actually realized that they could invert the convolution operation to reconstruct what the convolutions were taken from the data. So how this compression was working and to have a visualization back. And I mean, I really recommend watching the YouTube videos for some details because it's extremely clear. And then even before this, actually, it was improved later on in 2019, so 10 years later by the AlA team and all the Distill publication group. So they've thought of taking an individual neuron or an individual channel in a convolutional neural network and start looking at what type of inputs you could use to maximize the activation of that particular unit. And this is what now has been done more and more in the range of mechanistic interpretability, that is that we're trying to understand effectively how one neuron, what patterns activate, fire up one neuron, and how are actually these patterns then combined together. And one of, yeah. Sorry. Yeah. Yeah, it's true. You haven't been seeing the titles all along. Well, so as I was saying, so the gradient ascent method is a very powerful technique that it later on turned into feature visualization as a name. And here you're really trying to understand each of the little components. And I think in the next slides, yeah. Why is it going backwards? Okay, yeah. And you can do this also differently. So there is network dissection paper by David Powell. This is also another read that I suggest. Was actually focusing again on this unit activation, but looking per se at how at the activation patterns and propagating them back to the model. So and to the input image and visualizing them on the input image as a segmentation mask, for example, or what's commonly known as GradCam or CAM or class activation maps. And the difference between feature visualization and network dissection is that in feature visualization, you're inputting an image of noise. So you're trying to generate an image that maximizes the activation of the neuron. Whereas in network dissection, you're not generating an image, you're just generating a heat map that will tell you which regions are maximizing the activation of one unit. And as I was saying, feature visualization has then been further taken and further analyzed into the circuits work also by the same people, where you're actually trying to combine these activation patterns and how they work throughout the network. So how they interact with the weights of the model and how this leads to, for example, the detection of early curves on the right, on your left here. So the identification of these patterns that look like a curve and how these are combined with lines and other patterns that are learned by other units into more complex shapes of curves. And you can see actually all of these patterns throughout the network and also how they used then to recognize object parts. For example, the wheel, the steering wheel of a car, or the tires of a car, and other round shapes. Okay, now going a step higher up, and I mean, I'm putting this as a higher up step because it's just, I would say that they're almost equivalent, but they're giving very different type of outputs. With mechanistic interpretability, we're trying to get a global understanding of the model, what the model is doing. And this might not be very useful to a clinician, for example, but it can be useful for us developers to identify all of these problems that might be in the model. With post-hoc explainability, we're really trying to target instead the end users, and we're trying to generate explanations, for example, for a specific input sample, so in a local of the input, in a locality of the input. And we want to realize which input features are actually explaining the model outcome. And the most common form is saliency. So you just look at the derivatives of the output with respect to the input. I think this was one of the first methods, and it's the simplest and most intuitive to understand. It comes with a bunch of problems, but it's also good to have to know how things started and how they developed into more complicated methods like integrated gradients, for example. And here I have put a summary because I think it's helpful to categorize all the post-hoc explainability models at least in 4 categories. So the first category is feature attribution. So looking really at the class activation mapping. or external perturbation masks. If you want, it's a fancier way of looking at the gradients. And some, at the second line, you see some of the same methods applied to histopathology images, just to have a look of how applying these techniques that were mainly developed for for the computer vision domain, how they apply to the medical image domain. And well, feature visualization, we talked already about it, and there are other two branches that are concept attribution and surrogate models. And on concept attribution, I think we have a tiny bit of explanation that will come also later. But for surrogates, the idea is really similar to what I was explaining before. You have your linear decision function that is a complex curve, and you're trying to find a surrogate model that can replace your model in a locality, and that is easier to interpret because you're using an inherent interpretable model as a surrogate. So that's kind of the main take about these methods like LIME. These are some of the examples of how, when you actually apply LIME to medical images, it looks like. And I'm also showing some of our work that started from those building blocks and try to create something that is easier to adapt to the medical image domain and also produces more interpretable outcomes in the end. So moving now, when we go to concept-based interpretability, we're actually looking, instead of looking at what input features were used to explain the model outcome, we're now looking at what high-level concepts are used to explain the model outcome. And the reason of this passage, this shift moving from input pixels to high-level concepts is because in some cases, having a heat map of the region is not sufficient. You don't know what type of pattern actually in that. Even if you see the pattern, you don't know what's the characteristic of that pattern, what high-level concept is that pattern responding to. So in some cases, you might have very fuzzy heat maps, and I think I was showing it in the previous slide here. So if you look here, these are very different patterns in histopathology. I don't know if you are familiar with the domain, but you can see that this is much more narrower than these images. But these were obtained for the same model, for the same method. So in some cases, you have a very fine-grained explanation about what's activating the model, what's causing the prediction. In the other case, it's a bit fuzzier, and you don't know anymore whether it's the nuclei cell or it's the stroma or it's something else. And so with concept-based interpretability, you can structure your data into high-level concepts that are more understandable or easier to understand by physicians, for example, or for domain experts. And you can try to estimate what's the impact of those concepts to the prediction. And this translates into, for example, asking what is the relevance of stripe texture when you are classifying a zebra. And if you want, that's what distinguishes a zebra from a horse in the end, right? So it must be very relevant. So this was an overview, and it was very quick, but I wanted to go through all of these methods because I think it's important to have an interpretability compass in the field of interpretability, because really the technique you're using depends on what's your end goal and who's going to be the user, who's that interpretation, that explanation built for. If it's built for physicians, you should first listen to the requirements. What are they available to work with and what they think is going to be useful to them. And if it's for debugging, probably you want to look at different type of techniques than what you would use for working with physicians. And so I think this is a map that I've built some time ago, but I still find, I think still valuable and useful. And it's really this compass trying to understand what you want to have in the end. Do you want to have user-friendly explanations? Do you want to understand each and every component of the model, or having specific visualization for a single input? All of them are equally useful, and there are plenty of other things that we could have talked about. So I'm happy to discuss all the details of each technique in the specific case. But I think understanding, first of all, which technique to start with is the most important part, because then once you've taken these techniques, you need to adapt them to the specific field that you're working on and the specific type of images that you're working on, and the domains and the requirements of that application case. And if you want to hear more and more details, you can register to the course. We have a course going on for the project that is funding my postdoc, is AI for Media. And you can register and you will get access to a lot of content and videos and explanations, and also tutorials, so really like Colab notebooks where you can replicate code, and they should be easy and straightforward to run. And just give me 5 minutes to say what's next after this, because this was really interesting and very introductory, but I'm still doing a lot of research and I cannot stop talking about it. So I think what's after all of this, so once we get to that intermediate point in the map, what can we go for? What can we aim for? So one is last type models. So trying to build a model that is interpretable by definition, that it has it in the interpretability constraint. It has an interpretability constraint in the optimization function. So you want to be interpretable at the same time as solving your main task. There is also the introduction of causality constraints in the optimization function. That is also an active area of research, trying to generate counterfactual explanations of as a postdoc method, but also building models that already have those causal links. And finally, I think that's been the focus of my past year's postdoc, is really using interpretability for data and knowledge mining. So we have the benefit of working with extremely challenging cases for which we have, in some cases, still limited knowledge about. We don't know exactly how the human body works entirely. So can we use models for which we have very high performance to mine the information that is extracted by this data and learn something new? Going through all of them. So the first one is really some advertisement of something that is not my work, but it's some work that I find extremely exciting, that is explainable boosting machines. Have a look at it. You will see that it's mostly built for tabular data. And in some cases, it's extremely useful, and it's worth really trying and applying it as much as you can, guys. But I think the challenge here is really to move this type of models to something that is not tabular data, to something that is structured data, like our images or 3D volumes and stuff. So I think that's really some nice way to get to the top of something new. As for the introduction of causal explanation and counterfactuals, I think it's important to take away from this slide that most explainability methods are evaluating the influence of some feature to an observed outcome, whether this feature is explained in terms of the input pixels or a high-level concept that can be in the embeddings. But in the end, we are not able to actually estimate how would the model output change if we were to intervene in the learning of that feature. And I think that is something extremely interesting to look at, and because it would allow us to really answer a different type of questions. That is, for example, what would the gene expression of this cell had it been like, or had looked like, if the cell had been treated differently? So how, if we had considered, had this patient been a woman, would the reaction that we observe in the end have been different? So I think having this interventional expectation is extremely interesting, and that's probably the next step also, the generating counterfactual explanations that are much more robust than in the identifying salient inputs. Finally, and I think I'm over, it's data knowledge and mining. So using interpretability to discover relationships that we are not really familiar with yet. We don't know enough about. And one of them is, for example, can we actually correlate molecular subtypes? So if we look at the biological information from a patient, that is gene expression, can we actually correlate that with histologic tissue appearance? That is something that is much cheaper to obtain and is much more available than what we have now for patients. And this is some of my recent work. In fact, you can use something called attention, and there are ways of interpreting attention distributions in models, and you can look at how actually the model is using this attention to predict something that humans cannot predict from images. So looking at a tissue staining from a microscope, you're able to predict the ranges of gene expression of a bunch of genes and connect them to which images were they actually used to predict these genes. So for example, here you see that for high is a gene expression of this particular gene. There are some images that are retrieved, and funny enough, we know that this gene causes a particular appearance in the slides that is exactly what you're looking at here. So even if you're not familiar with histopathology, you can trust me because I'm telling you that for this high expression, you observe patterns that you would expect to see. And if you apply this to images and to ImageNet, you end up also in very nice and interesting cases where you can discover concepts that are learned in the latent space of a model, and then backtrack them to the input images and identify these striped tissues, for example, the striped textures that we were first inputting as a user, wanting to know what's the relevance of the striped pattern to the output. Well, you could also discover it in a non-supervised way without knowing that actually the stripes might be important. And when you do this, you can also do other fancy things, like, for example, analyzing the data set, and you would end up again in that low, long tail distribution with samples that have maybe misleading annotations, wrong annotations, they have a strong distribution shift, or they have labels that are like more than one label that is correct. So yeah, that concludes a bit the tutorial. I hope I was on time. I didn't. Okay, fantastic. It's a great time to be alive. I wanted to really steal this tweet. I wish I had said that, honestly. So I think all of this with also, if you consider the coming in of artificial general intelligence and all the discussions going on these days, I think interpretability as part of the AI alignment is becoming more and more relevant, and there are new questions that are arising. So we're not really saturating the field. We just need to be focusing on new questions that are also very important. And I mean, since it's been the topic of my postdoc, I also think that using interpretability to discover new pattern and focusing on scientific discovery is also a very exciting aspect of working with these powerful models, because they can probably find patterns that we don't expect, we don't know about, and we don't expect them to find.